part we can put down to the, so say if ms equal to s, okay, so how about this? Let me call this is m2, this call it m1, okay? So this is m1. So this is m1s, okay? So if we have m2, then you can see if we repeat the whole process, basically this has the, this is m2. It has the slope is equal to positive. And then for this one, the m2 has the round out the space. Let me draw it here. So if this is a 90 degrees, so this is for m2. Okay. Okay. So this for m1. Then we can try this one. This one is a first order system has time delay, and that system is first order system without any time delay. And the time constant for this is equal to t. And by definition, if you still remember what is the time constant means, time constant basically is if you give the unit step input to such system, then you know the system usually will try to begin like this, right? The response, time domain response will be like this. When the magnitude of the output response reaching the point 6, 7 something, I think that is the magic number, log E or E, I forgot. Okay, so that one, about the points 6, 7. So when then the time spent to reach this magnitude of the control input is called defined. It's defined as the time constant of the system. So basically, time constant of the system is to mark when the magnitude will reach a certain threshold. So this T, time constant, also can be served as an index to system performance. And the role is pretty much like rising time for I think rising time. Okay. So for system to be very fast, then the time constant is usually small. If time constant is kind of large, then we say the system is slow. Okay, so that is the definition here. So now for this one, then we can try. And so here we introduced s equal to j omega. We put into calculation 1 equal to j t omega. So therefore here we have the magnitude. We calculate 20 log 10 of omega. J omega will be equal to 20 log 10, 1 plus, this is magnitude, okay, J omega, and that one, let me keep writing here. So that is log 10. This one basically is equal to 1 squared, 1 plus t omega squared. We first calculate the magnitude, and then we take into the log equation here. So basically here that is equal to, you know, the log a over b is log a minus log b, right? And for this case, a equal to 1, so that means the log 1 over b equal to 0 minus log b. So here we take this equation here. So basically this is equal to minus 20 log of this. Okay. And then here the log square b, we have equation is the log b 1/2 And usually this exponent we can take out the log. So basically that is 1/2 this one. So for this case, it's minus 10 log 1 plus t omega squared. Okay. 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 And then keep that in mind. Then we can calculate phase. The phase again is this one, 1 plus j t omega, and this one basically equal to 0 degrees minus phase of 1 plus j t omega. So 0 degrees minus arctangent t omega over 1. So basically this is minus arctangent t omega. Okay. So for the two, and then I'm going to base upon this one and based upon these expressions, and we can see how much we can explore the drawing here. For this one, the plot will depend on the magnitude of the t. And so here we kind of do this schematic sketching of the plot. And so here we can try 3 extreme scenarios for the value of the omega and as compared to t. So here we can put into this. So based upon this, we can see the value of the omega and then the value of the 20 log m and the angle. Okay, so say for omega is very small, then we'll see what happens. When omega is very small, basically this term will be gone. So log 1 equal to 0. So basically this value is almost equal to 0. Okay. And for angle, when omega is very small, so basically arctangent of 0, basically that is 0 degrees here. Almost. Okay. And I think it's better way to describe is this t omega together. So that is my mistake. It's better to describe t omega is very small, okay, together in this one we're guaranteeing. And then, for example, when t omega is equal to 1, when t omega equal to 1, then this magnitude, we can do the calculation here. So basically that is equal to minus 10 log and 2, right? Okay. We plug into here, we plug in t omega equal to 1. And what is this number? And this number actually equal to minus 3. Exactly. Okay, and that is called minus 3. And again, that is, in terms of this one, we have a unit dB. So basically here, this is has a unit dB. Okay, so here is dB here. So minus 3 decibel and minus 3, and that's the magic number. We define, if you remember, we define our bandwidth is at
0.7.
This number back to here. Let me do this one here. So this one, 1 over square cube is on the scale before we take into the dB unit. So for this one, if we calculate 20 times log 10, 1 square cube, we see what is this one. This one actually corresponding is minus 3 dB. Okay, so basically here we indicating this one is when t omega equal to 1, that basically here we calculate is the bandwidth for omega. Okay? And then we continue. So for this one, when t equal to 1, and arctangent of 1, so basically that is minus 45 degrees, right? Okay. And then for this one, when T omega is very large, say go to infinity, then basically 1 plus a big number, so that would be equal to minus 10 log, and 1 plus big number, so basically we can approximate it by the big number here. Okay, so here we drop 1. So this one we can calculate basically is equal to minus 20 times log T omega. Okay. And then for the phase, when T omega is very large, basically this approaching to the arctangent of big number basically equal to 90 degrees. So it is minus 90. So for this one, we can conclude, we can try to draw it is like this. Let me try this first. When T omega equal to 1, so that means corresponding to is when omega equal to 1 over T. Okay. And then that value corresponding is minus 3 here. So we simply point 1 point here. Okay. And for this one, when T omega equal to very small, that means omega equal to very small. So that means approaching to the left-hand side of the domain, the value equal to 0. So 0, let me put 0 here. So that will be starting from here. Okay. And then when go to infinity, so that means once we go approaching to the right-hand side of the domain, the value basically is the larger the omega, the small, and that approaching to it is kind of approximated by a straight line, right? So basically approaching to here, this behavior that is kind of the approximated by a straight line, kind of the trend in a straight line. Okay? In this range, for this range here, you can see that pretty much remain constant. So that means for omega is very small, and the trend of the curve is just like the dot here. Okay, so basically here what I'm drawing the dot is working as the asymptote for plotting the magnitude. So here, why not here? Usually our practice is this. We simply draw the asymptotes for the two extreme scenarios, and then using asymptotes as the approaching behavior of the curve. And then here we simply try to match the trend in along with the asymptote. So here the curve usually we can draw is this. Okay? So when I go to infinity, then go to the extreme situation that basically will follow asymptotes. And due to the transition situation that is marked by this point, right? So basically here we simply make a curve and smooth change from there to here. And usually this is the curve, with a curve like this. Okay, corresponding to here is minus 3 dB. Okay, so which means the difference between the intersections, intersections of the real value and this is minus 3. This might equal to 3 dB here. Okay, and this one at this particular frequency, and that for this case is omega, t omega equal to 1, and that is this case. And or equivalent say omega equal to 1 over t. And this one, most of the time people give a special name to this, called the omega c, and they call it corner frequency. The frequency corresponding to the intersection of the two asymptotes, the corner frequency. Corner frequency at which your asymptotes, your estimation based upon asymptotes will be always for this system on 3 dB larger than it's supposed to be. Okay, so that's just kind of the spatial name, the corner. So again, for this kind of the linear systems and even later on higher order systems, our practice is to first we manually derive the information for gain and for phase, and then from this one we simply prepare ourselves to draw asymptotes, and then from there we get the corner frequency information, and then we try to sketch through it. Yes.
I'm sorry, when you draw the horizontal line at 0, is that just because for small?
Yes.
Like it's essentially just 0.
Yeah.
Way, right?
So yeah, as long as we keep that our focus in the left-hand side, then that pretty much will remain constant 0. Okay. And for magnitude here, then basically we have the 0 degrees, so let me label it. So here is 0 degrees and 45 degrees and 90 degrees minus. Okay. So again, here we can draw in the phase. We also have the asymptotes. When omega is, say for this case, when omega is very small, so basically the asymptotes for phase will be like this. And for omega become very large, so 90 degrees, and that one basically is this. Okay, so that is the asymptotes here. Okay, and then at the 45 degrees at the corner frequency here, the angle is 45, so the curve must pass that point. So here at the small omega, the behavior is governed by a constant 0 degrees, and when omega becomes large, the angle is pretty much 90 degrees. So transit from there to here, and again, here we only sketch, and I really doesn't matter. Here you can see I didn't label the scale. So basically here we can try to transit and with a kind of the beautiful smooth curve. Okay. The people were only concerned for this sketch is about the information at the corner frequency there. As long as you label precisely, then people won't criticize much about transitions. Okay? If you are so concerned about the drawing, say, hey, if this is a corner frequency, if I want to calculate what is this value at the tenth of the corner frequencies for magnitude and for phase, then how would you answer these questions? Then you simply go back to here, you simply introduce omega. So in this way, if omega equal to tenth of the corner frequency, so basically by definition, corner frequency is 1 over t, so here omega is 1 over 10t. You simply introduce this number to here, you redo the calculations for magnitude and for phase. Then you should have a number here. Then in this way, that will help you to have more point for you to trace the curve. Okay? So that is a way to calculate in detail. If really you are picky, then you can, but for yourself, you can add more points just nearby the corner frequency range, and then you can do better job for drawing. But usually we can ignore this stuff.